That lab is going to be on neutron flux. It's just one lab. It is strictly extra credit. And I'm going to have everybody meet at 10 a.m. and we'd be out of there by 12. If I have a large number of students that want to go, I might have to break this up and have one group at 10 a.m. and another group at 1, just for staffing at URI. And I'll probably touch base with you on Wednesday of this week for who wants to go. And again, this is strictly extra credit. If you attend this lab and just witness and do the lab, I'll give you extra credit. If you do the write-up for the lab, I will give you extra credit. Strictly optional for Tuesday of Thanksgiving week. And then the week after Thanksgiving, we're going to have, again, a Tuesday where we're going to do 3 labs. And then Thursday that week, we're going to have the same 3 labs for the balance of the class. And then that's it. I'm going to pick a date probably at the end of the following week after that. And what I've always done is I will allow you to submit a lab of your choice. There are 5 that are due for sure, a 6th one if you do that one for extra credit. I'll allow you to submit 1 lab to me and I will thoroughly grade it, and then I'll give it back to you. If you get a, let's say, a B on the lab and you're happy with the lab, fine, because I'm happy with the lab. If you want to look at that as seeing how I grade labs, that would benefit you from the submission of the balance of the labs. And I'll also permit you to resubmit that 1 lab again to get a higher grade on it. And I'm probably going to pick either the Wednesday or Thursday after the last round of labs at URI. I'll also give the option of when you submit the labs, it can be a group lab, it can be an individual lab. Usually when we start off, one of the first experiments we do is neutron activation, determining half-lives. But unfortunately, we can't do that this time due to the testing that they have to do for the NRC. And those labs, you're typically 2 or 3 partners per setup. The ones that we're going to be doing this next week, if there are 12 of you in the class, everybody's going to be doing the same lab at the same time. So again, you could write 1 lab up for all 12 of you. Whoever's name is on the lab sheet, everybody gets the same grade. So I'd encourage you, if you are adding people, to make sure that they're doing something for the lab. But you could break it down. I could have 12 individual labs submitted. I could have 3 labs with 4 people each. It's however you decide to do it. Okay. Any questions on URI or the labs? I'll go over later about when that date is due for the 1 lab you can submit for sort of a preliminary grading. Anything else on that? And remember, this is at the Narragansett campus tomorrow. It's not at the main Kingston campus. In fact, if you go down 138, you'll go right by the main campus, so don't turn in there. Okay, I don't think I had anybody volunteer to put the Reactor Theory quiz on the board, at least when I asked earlier. Is anybody interested now before I put mine up? Okay. Okay, I told you we had our earlier beryllium, U-233, U-238, fuel moderator mixture. If you remember some of the information that we had before, we know that K effective is 1.62, buckling was 0.206 centimeters to the -1. Little d was 0.91 centimeters. Okay. In this particular case, we asked you to take this fuel moderator mixture and place in a cube. Okay. We immediately start with the general diffusion equation. Which is del 2 flux plus B squared flux is exactly equal to 0. And we know this general diffusion equation is good for any fuel moderator mixture in any shape you could potentially put it in. So when we see cube, we know cube is a type of rectangular solid. And for a rectangular solid, our del 2 operator becomes this, the partial to the 2 of dx2 plus d2 of dy2 plus d2 of dz2. If I apply that back into here for, again, the del operator, this becomes d2 flux. Okay. So as soon as you see this, you know that this now is, instead of the general, it is the specific diffusion equation for any rectangular solid. Okay. Now, how would you solve this? You would solve this using boundary and initial conditions. Okay. If you did that, I'm going to go back up here to the top. Then this becomes flux, which we know is going to be a function of x, y, and z, is going to equal flux max times the cosine of pi x over x 0 times the cosine of pi y over y sub 0 times the cosine of pi z over z sub 0. Okay. So this again is the flux equation for any rectangular solid. We also know that buckling squared for a rectangular solid is pi over x sub 0 squared plus pi over y sub 0 squared plus pi over z sub 0 squared. Any rectangular solid you have, you know that this is the specific equation to define buckling. And this again is looking at shape only. Okay? We also know, since we have a cube, that x sub 0 is equal to y sub 0 is equal to z sub 0 is equal to x sub 0. So we can go back and substitute in here, and I chose to let everything be equal to x of 0. So I have b squared is equal to pi over x of 0 squared plus pi over, I'm going to substitute for y sub 0 since it's equal to x of 0 squared. Same thing again for z sub 0, since I know that's equal to x sub 0, I can do this. If I look at this, this is one of a kind. So when I add, I can add like items. So if I add this to this to this, I have this is equal to 3 times pi over x of 0 squared. If I then take the square root of both sides, I have b is equal to the square root of 3 times pi over x sub 0. If I cross multiply, I have x sub 0 is equal to the square root of 3 times pi divided by b. Excuse me. We know from our prior quiz that b was 0.206 centimeters to the minus 1. Square root of 3 is square root of 3. Pi is, whenever it's outside a trigonometric function, it's regular pi, 3.1416, etc. So I had that come out to be 26.4 centimeters. So now we know the extrapolated boundary in the x direction. That's also going to be extrapolated boundary for y sub 0 and z sub 0. Any questions on what we've done so far? Everybody tracking with me? Okay. Question? Tracking? Okay. Everybody following me? Okay. So, once we know that, we can go back and we know that x of 0 is equal to x of g plus 2 little d. So x of g is equal to x of 0 minus 2d. X of 0 was 26.4 minus 2 times little d was 0.91. So I had x of g equal to 24.6 centimeters. Again, you might have a slightly different number depending on how you round it off, what number you use for pi, how many significant digits you use for the square root of 3. But we also know that x of g, because it's cubed, is equal to y sub g is equal to z sub g. And what I was after was, what was y sub g? So that's my answer for y sub g. Any questions on that? Okay. Next question I asked was, I wanted you to evaluate the flux at a point inside a reactor. In particular, I asked you for the flux at 7, minus 5, and minus 8. And those are the values for x, y, and z. And we know our specific equation was flux max times the cosine of pi x over x of 0, cosine of pi y over y sub 0, cosine of pi z over z sub 0. But we know x sub 0, y sub 0, and z sub 0 are all the same. So if we plug in those values, which was 26.4, 26.4, 26.4, when our maximum value for the flux was 8 times 17, excuse me, 8 times 10 to the 17th neutrons per square centimeter per second. All we do then is substitute in the value for x, 7, y, minus 5, z, minus 8. And remember, whenever you do this, anytime you have a pi inside a trigonometric function, that pi is exactly equal to 180 degrees. So when I did that, this becomes 8 times 10 to the 17th neutrons per square centimeter per second. This becomes the cosine of 47.7 degrees. This becomes the cosine of minus 34.1 degrees. And this becomes the cosine of minus 54.5 degrees. I then do this trigonometric function, and I get 0.673, 0.828, and 0.980. Excuse me, 580. When I multiply all those together, and my flux at that point is equal to 2.61 times 10 to the 17th neutrons per square centimeter per second. So inside our cube at this specific point, this is the flux at that point. Any questions on how I did that? No questions. That's good. So everybody's got that. All right. The next thing I asked you was, and I'm going to erase everything above here. And I asked you, what is the neutron current density in the plus y direction at my point of interest? So we could even put that in. And we know from a definition of neutron current density, it's the flux at that point divided by 4. And if this is a plus, this is a minus. There's any number of different terms you can use there, from 1/6 times the macroscopic cross-section for scattering. You can use a variation of d, which is a diffusion constant. But probably the easiest one to use is little d, which is the extrapolation distance, divided by 4 times the partial of the flux with respect to the axis that you're interested in, which is y, evaluated at that point. Okay. This part is easy to fill. We just solved that. The flux at that point is 2.61 times 10 to the 17th. Little d is 0.91. Now we just have to do this other guy. So if we look at the partial of the flux with respect to y, we're going to evaluate it at our point of interest, which is this point. And again, in looking at this, by using this script d, that tells us that the flux varies as a number of variables. And in particular, we're interested in just one of them, which is y. So if I do that, I'm going to do this on my flux equation. So I have to take partial derivative of this with respect to y. Whenever we do that, you treat everything that does not have a y as a constant. So this becomes the flux. You put flux max here. Flux max times, there's no y in this, so this stays the same. I move this up since that didn't change. Okay. Now I'm going to do the partial of that, and that becomes minus the sine of pi y over 26.4. And then I take the derivative of what is inside with the y, which becomes pi over 26.4. Okay. If I go back in and substitute values, this guy was 7. This guy was -8. This guy was -5. If you notice, this is the same as this. This is the same as this. That's why I would recommend you keep those numbers when you do that. The partial flux with respect to y evaluated at our point of interest is going to be the flux max, which was 8 times 10 to the 17th, times this cosine, which is exactly this. This cosine, which is exactly that. Okay. And this becomes minus the sine of minus 34.1 when I did this. And I had that come out to be, this comes out to be a minus, times a minus is a plus. And this divided by this was 0.119. So when I multiply all of this out, this is the value that goes back into here. And when I did that, I had jy plus evaluated at the point D. This divided by that, I had as 0.6525. And I had all that come out to be minus 0.047. So that my final answer was 0.605 times 10 to the 17th. Again, units, neutrons per square centimeter per second. And again, that is a vector quantity. So inside our cube, I've opened up a little 1 centimeter by 1 centimeter window inside here. And I'm looking at what's going through that in the plus y direction. And I just calculated that value. Any questions on what I did or how you would do this? Everybody think they got it?
Professor, just real quick, can you go over how you got the B value just one more time for buckling?
Okay. Any questions on this though before I erase it? Everybody feels comfortable with this? Okay. Okay. If you remember, are we talking about how did I come up with the actual number for buckling, or how did I come up with the expression for buckling?
Just the number for that specific problem.
Okay. If you remember, we went back originally and we found K infinity. And then we went through and we found volumes, we found macroscopic cross-section for transport, we found macroscopic cross-section for absorption, we found thermal diffusion length, and we used all those. This was the first step. Then we had a second step, and we came up with an expression for buckling, which was this. And that was the second quiz that I gave you on this. And this was also the second example problem in the book. So this defines buckling from fuels and moderators only. So when you go through K infinity, you go through these other steps, you ultimately come up with buckling. And this buckling is only a function of the fuels and moderators that you have used. Then you go and you place. Notice up to this point, we've said nothing about a shape. We don't know what we're putting it into. Infinite slab, cube, rectangular solid, cylinder, sphere, whatever it could be. We then look at the general diffusion equation that we've developed, and we can come up with an expression for flux depending upon what this del 2 operator is, which depends on the shape that you put it in. Okay. For each shape, there is a specific buckling equation unique to that shape. So if an infinite slab, we know that that buckling square is pi over x sub 0 squared. This only exists for an infinite slab. And this defines buckling by shape. So whenever you have those materials, you found out buckling from looking at just the materials. Then whenever you go to put it in a shape, in this case we picked an infinite slab, we know that buckling is equal to this for an infinite slab. So we can come up here, and if we put an infinite slab, this buckling is also equal to this. So this is equal to this because they're both equal to buckling squared. And this is how you couple materials to a shape. You do it through buckling. We did that example before. So if I had told you you were putting this into a rectangular solid, automatically we should know that buckling squared is equal to this. And if I took this material and put it into a rectangular solid, then this is equal to buckling squared, which is equal to this. So this buckling for a rectangular solid ties back to the same buckling value that you got for the materials. So these materials, it could be 3 fuels and 2 moderators. Doesn't make any difference. Whatever you come up with buckling from that mixture of fuel and moderators, it is what it is, defined by K infinity and these other things to come up with this. As soon as I put it in a rectangular solid, you know that buckling has to equal this, so that now this and this are coupled. In the case we just had, this was a cube, so this equal to this equal to this, so this reduced to 3 times this. If you have your textbook handy, this here so I don't block the screen, so let me know if I do. So does everybody get a feel for that? Hopefully, because I'm going to erase a little bit of this. Okay. Let's say I took this same material and I put it in a sphere shape. Okay? And again, I'm still using my beryllium, uranium-233, uranium-238. And I put it in a sphere. Does this equation change at all? Yes or no, and why? Anybody?
No, because that refers to the materials.
That's right. This does not change because this is due only to materials. Okay. Now we have to go back and look at how we're going to modify our general diffusion equation. And as it turns out, for a sphere, my del 2 operator becomes
Professor, could you use a darker marker? We can't really see that.
This is in your book. So your del 2 operator for a sphere becomes D2 flux D. Let me just. So my del 2 operator becomes D2 flux dr2 plus 2 over r times d flux dr, and they would have to add in the rest of it, plus d squared flux is exactly equal to 0. So I've used my del 2 operator to modify this, and this is the equation that I would then solve to come up with the flux in a sphere. That gets to be rather complicated, but the one thing that if you looked up you could tell is that buckling squared for a sphere is pi over r sub 0 squared. So if I put this material in a sphere, this would be the value that I used. And I already know that this buckling from before was 0.206. So I now know this, so this would be 0.206 squared, because that's buckling squared. Now I have one equation, one unknown. I can find R sub 0 and go from there. If you look at putting it in a cylinder, any questions on this? This is a little heavy duty for you for math, so I wouldn't expect you to do that. If we look at a cylinder, and again, if I put it in a cylinder, does this B2 equation or value change? No, because this is due to materials only. If we go back to our basic general diffusion equation, we have this. So I have to find the del2 operator for a cylinder, and it comes out to be D2 dR2 plus D pull this up because I'm having trouble looking over my shoulder here. This is 1 over R D dr plus D2 dZ2. Because remember, a cylinder has a Z direction and it has an R direction. So this is the del operator for a sphere. So I have to put that back into this equation. So this becomes and we solve this using boundary and initial conditions. And this comes out to be, you probably have, at least I don't think you're, is anybody here familiar with Bessel functions in your calculus yet? When you go to solve this, the flux turns out to be equal to flux max times J sub 0, 2.405 R divided by R sub 0 times the cosine of pi Z over Z sub 0, where this is a Bessel function of the first order zero kind. So this is a function that you could look up, it'd be tabularized, just like you could look up a function of the cosine. This is not going to be on your calculator. You'd have to go to a mathematical handbook to find this value. But just like if you went into a handbook, you could find the cosine of 44 degrees, you could find the cosine of 44.1 degrees, any of that type of thing that's tabularized, you could find the Bessel function that you're interested in. So this is the equation for the flux that is specific to a cylinder. And if we go back and take this to look at buckling.
Professor, what does it say after cosine Z over Z 0?
This is This is from
Oh,
another,
alright.
okay. And then, as it turns out, the buckling in this case is so if I gave you something in a cylinder, you would automatically know you could still find buckling squared this way for just the materials. If it ended up being in a cylinder, this is the equation that you would resolve from the general diffusion equation that you'd have to use. You can't use that right now because you don't know what a Bessel function is. But this is buckling for any cylinder. So again, this is the buckling for my cylinder, and this ties together shape. So if I ask you to put this material into a cylinder, this buckling squared is exactly equal to this buckling squared. And you could be off and running to solve that for a particular cylinder. Any shape you could potentially come up with, we could solve it taking the general diffusion equation to a specific diffusion equation. And there is a specific buckling squared value for any shape. A lot of people that were mathematicians got their doctorates coming up with what those shapes are. And then you couple shape to materials and go from there. You feeling comfortable with that, or you want to do a little quickie problem? You're asking where does the 2.405 comes from? It has to do with the boundary and initial condition when you solve that equation to come up with this. It's like, why did what we did with an infinite slab come up to be a cosine? That is a function of that specific differential equation. When you solve it, the solution comes out to be cosine. In this case, it comes out to be Bessel function and cosine.
Can we run through an example with the cylinder?
That's going to be I'm not going to give you a cylinder on the exam. You don't have the ability to do that right now unless you have a mathematical handbook.
Nope, I'm satisfied with that. Thank you.
Okay. If you want to look just any rectangular solid, we could do something like that very quickly. But if you feel comfortable with what we did today for the cube, I think you're in good shape.
Can we do an example?
Okay?
Okay, before you erase that, can I just ask a question real quick?
Yep.
In our diffusion equation, we have flux max J sub naught. Is that a vector quantity, that J?
Right here,
Yes.
this little zero here goes back to the type of Bessel function that it is. So I could have had J1, J2, it could be anything. This defines the type of Bessel function that it is.
Okay, thank you.
If you haven't been exposed to Bessel functions, I could spend the rest of the semester just probably going over that alone. Remember I chatted with you earlier, I said, you're going to learn all the basics that you really need to know about nuclear engineering, frankly, in Professor Abel's course last spring, assuming he went over everything on the syllabus, and things that you're going over with me this semester. If you go on to get your baccalaureate degree, or if you decide to go further to get your master's or whatever, the things that you've learned now are not going to really be changed by going through an advanced degree. But what you're going to learn is different mathematical techniques and approaches and equations to solve situations that you might have if you did have a sphere or a cylinder or some really unique shape. You're going to apply different math tools to the basic understanding that you have on this course. It's hard for me to explain that to you until you go up to UMass or wherever you go and pursue a baccalaureate degree. You're going to go back and say, oh, I remember that, and now I have much better tools because you'll have taken calculus 3, differential equations, etc. So now you have a whole bevy of tools to solve equations and to better understand what's going on. Does anybody know what a Monte Carlo solution is? Okay. Before I go back to the problem very quick. It might turn out that you have certain equations that are very difficult to solve. And what you might end up doing, and let me see if I can find one very quickly. I'm just going to sort of invent this. Let's say you had that equation to solve, and it is an equation. That is really messy to solve. So the Monte Carlo technique says select an x, and you put it into this equation. So you put it in here, you put it in here, you do all that algebra, and you come up with a value. Let's say this value comes out to be 14.4. You put it in this side, you do that math, and let's say this comes out to be 18.6. So this does not equal this. So your guess for x was incorrect, but you can guess then another value for x. Let's say the next value you have x go up. You plug that back into here, and maybe this number comes out to be 16.4. When you plug it in on this side, it comes out to be 17.1. So is this x the answer? No, but it's getting these two values closer. So you'd guess again, and you'd guess again x to go up again by a smaller amount. And let's say the next time you solve it, this came out to be you have solved this equation by guessing a value and making one side ultimately equal the other. This is called a Monte Carlo solution because they're not really programs or calculators that are designed to do that. And this came out from Monte Carlo from gambling. I don't know the exact history of it, but I know on occasion you will find yourself stuck and you just can't solve it any other way other than to do this type of solution. Guess and check. Okay, hadn't heard of that, but that's true. Okay, let me go back to, any questions on that? Okay, let me just randomly pick a rectangular solid. And I'm going to tell you flux is x, y, z. And let's say this is 2 times 10 to the 20th times the cosine of pi x over 14. It's a cosine of pi y over 18 times the cosine of pi z over 22. So this is a specific flux equation for a rectangular solid. And then I might ask you, what is the flux evaluated at a point? So why doesn't somebody give me three numbers and they could be plus or minus?
2, -3, 6.
That looks tough. I don't know if I can do that one, but we'll try it. Okay, so I want to know what is the flux at this point. So I'm going to evaluate this at cosine of pi x, which is 2, divided by 14, cosine of pi y, which is -3, over 18, that's cosine of pi 6 over 22. And again, these pi's are all equal to 180 degrees because they're in a trigonometric function. So hopefully you're using your calculator. Yes?
Two things. One, the camera's pretty blurry right now, so it's difficult to see the board. The other thing is that the denominators that you chose, those are just the x sub naught, y sub naught, and z sub naught, like lengths.
Correct.
Those will all be in centimeter. Okay, thank you.
This is x sub 0, y sub 0, and z sub 0. I took it from a general to a specific flux equation by putting in the numbers. If I'd have left this as x sub 0, y sub 0, z sub 0, then this would be a general flux equation for that rectangular solid. As soon as I have all of these numbers in there, then it's a specific flux equation.
And you just gave us those numbers so we didn't have to calculate what they were. Is that
That's right.
okay?
That's right.
Thank you.
So this guy is going to equal cosine of, and you can do these with me, or hopefully you can do them yourself. But let's do them together, make sure we do this correctly. That's 2 divided by. So I get this is the cosine of 25.7 degrees. This guy is the cosine of 30 degrees. And this is the cosine of 49.1 degrees.
Was it
Everybody get that?
cosine of -30?
Thank you. Okay. So then I would plug in and see what each of those are equal to. So 25.7. I got to be 0.901. Cosine of -30, I get 0.866. And find the cosine of 49.1. I got to be 0.978. If I then multiply this, the flux, times this, times this, times this, I have the flux at this particular point. And I get that value to be 1.53 times 10 to the 20th neutrons per square centimeter per second. Everybody get that? And when you do this, whenever you're defining these cosine values, I'd recommend you keep those values because you're going to find yourself when you do a partial, you're probably going to be using parts of that again. So is everybody good there? All right. Suppose I ask you then to find the neutron current density. Somebody, and we're going to pick at this point. Okay. Somebody give me an axis and a direction.
Z negative.
Negative Z.
Okay. Z minus, and again, we're doing it at this point. So we know this is going to be the flux evaluated at the point divided by 4. That's a minus. This has to be a plus. D over 4 times the partial of the flux with respect to Z evaluated at that point of interest. Okay. So we know that this value we just calculated, and it turned out to be that value. Okay. Since this is a different problem, I would have had to have given you a little d, or you would have worked your way there going through k infinity and all that stuff. So just for argument's sake, let's say that little d is 2 centimeters. Now we have to find this guy, and this, that's too light, let me go back. We'll partial the flux in the z direction. We're going to go back to our basic equation, and whenever we take the partial of this with respect to z, we take the partial of this with respect to z. So this becomes everything that is not z is in fact a constant. This is going to be 2 times 10 to the 20th times the cosine of pi x over 14 times the cosine of pi y over 18 times, we differentiate this, so it becomes minus the sine of that, which is pi z over 22 times, if we differentiate what's inside the cosine term, it becomes pi over 22. Okay. So when we evaluate this at the point of interest, the point of interest is this. So this is a 2. This is a minus 3. This is a plus 6. Okay. But we know this guy was the cosine of 25.7. This guy was the cosine of minus 30. This was the cosine of 49.1, so it's going to be minus the sine of 49.1. So this number is exactly this number, so we can put that in. This number is exactly that number. If I look at this one, I'm going to do, this is 49.1 degrees. I'm going to do the sine of that. And then this has to be a negative value, so this is going to be minus 0.756. And this guy becomes pi divided by 22, where that's pi is regular pi, 3.1416. I got that to be 0.143. So if I multiply this times this times this times this times this, that is the partial of z evaluated at that point. And whatever that value is, I plug it back into right here. And then I just do that algebra, and I have the neutron current density in the minus z direction at that point. Just that simple. Any questions on that? Okay. I am going to give you a quiz today that'll be due on Wednesday for this. And then I will spend some time on Wednesday. I'm going to try to finish up as much of the chapter as I can. If I have a little bit of time today, I might pick up. The next thing I want to discuss is blankets and reflectors. If I don't have a chance to do that today, I will definitely have a chance to do that on Wednesday. Any questions on what we've gone over today? Okay. What I'm going to do now is I'm going to go back and send you a quiz, and I'll go over it with you. Okay. Okay, I just sent you the quiz. I'll give you a minute or two to get it. Okay, if everybody has their quiz, this will be due at the start of class on Wednesday. I'm also going to give you today another quiz for nuclear material science. It'll be due on Wednesday. But on Wednesday, going forward to Monday, I'm not going to give you a quiz on either topic, because on Monday of next week, we're going to do the nuclear material science exam number 3 in class. And then I'm going to give you the reactor theory exam, which will be due, famous turkey leg exam that will be due after Thanksgiving. So if you have the quiz, I'd like to go over it with you. You have an unknown fuels and moderators mixture that has provided to you the following information: K infinity, buckling, and little d. And I'm telling you the specific flux equation for this rectangular solid is 7 times 10 to the 17th cosine of pi x over 20 times the cosine of pi y over 10 times the cosine of pi z over 30. And I want to know what is the flux at the point x, y, and z that I've shown, -5, -6, and -12. I then want to know what is the neutron current density in the plus z direction at that exact point. Then I want to know what is the overall neutron current density in the z direction at that same point. That quiz is worth 14 points. And then if we drop down to extra credit, if we go back to the quizzes we've had before where we had beryllium, uranium-233, and uranium-238, I now want you to put that mixture into a sphere. And then I want to know what is R sub G, which is the geometric radius of that material you placed in the sphere. Any questions on the quiz? Okay, why don't you take about a 10-minute break? I will see you back here at 5 minutes of 2, and then we're going to do nuclear material science. And what I'm going to do now is we're going to take it up a notch, and now we're going to look at 2-dimensional bending systems. Okay, so I will see you at 5 of. Any questions on the quiz? Okay, I'll see you at 5 of. Okay, let's do a little nuclear material science. And everything we've done before for bending has been pure bending, but with just one dimension. And so we started off, we had a member, and let's say we bent it like this to make it smile. And this was a positive moment. This is one dimensional. Now what we're going to do is two-dimensional. And when you do two-dimensional, you typically look at the cross-section, and then you sketch a grid, and then you put in a vector to show the direction of the multi-axial bending. So in this case, let's say that I apply a moment like this, and this is 10,000 Newton meters. And this angle is 25 degrees. So I am showing two-dimensional bending on this cross-section like this. When I do this, the first thing you need to do is to take this vector and to take it into its two component vector parts. And we know we can have a vector like that. And we can have a vector like that. Okay? This vector would be 10,000 times the cosine of 25 degrees. This guy would be 10,000 times the sine of 25 degrees. So knowing vectors like you do, you can break this vector down into its two component parts. And again, if I added this vector to this vector, I would come up with this vector. Sort of the key thing to note here is the direction of the main arrow and the direction of the curl. When we look at this, and I'm just going to isolate this one, this defines the location of the neutral axis. So in this particular case, if I transferred it back to here, wherever the neutral axis is, this will be neutral axis, I'll call this neutral axis 1, due to that one bending moment. And what we do is we let the curl your fingers, we're using the right-hand rule, point to compression. So in this particular case, I've taken multi-axial bending, I made it into two single bendings. This particular one, this will define the neutral axis, and where my fingers are curling down to defines compression. So everything below this neutral axis is in compression, therefore everything above it is in tension. If I go back and look at this guy, this defines neutral axis 2. So I don't know exactly where it's going to be yet, but I can come back over here and put in neutral axis 2. If I then look at how my fingers curl around the neutral axis, this points towards compression. So I know this side is going to be in compression, this side is going to be in tension. So as soon as you get multi-axial bending, you break it down into its two vector component parts, define each of the neutral axes, look at the curl, and immediately define tension and compression, tension and compression. When you get through doing that, hopefully you could see everything below this is in compression due to this. Everything above is in tension. On this one, everything on this side of the green is in compression. Every side on this side is in tension. So if I look at that, this area that's encompassed here is going to be compression and compression. So you know that this is going to be fully in compression. Likewise, if I look at this one, this side's in tension, this side's in tension. So everything here is going to be pure tension. If I look at this area, it has a tension component, it has a compression component. You don't know which way that's going to come out right now. We're going to find that out. Likewise, this corner is going to have tension and compression, so it's going to be mixed. We don't know what it's going to be, but that's what we have. Any questions about what we've just done? Okay. Since we've now defined, let's do this neutral axis first. We define a neutral axis and we define tension and compression. So in order to better see what's going on, and I'm going to erase this now. The first thing we need to do is for neutral axis 1, we need to define where it is. And we know it's the sum of the areas times their centroids divided by sum of areas. Now I made this very simple so we can go through and calculate this together. So if we calculate this neutral axis 1, we have two members. We have one rectangle and another rectangle. So this bottom rectangle is, if I establish this is my baseline, then this area is 2 by 6. The height of its centroid is half of 6, which is 3. The second guy is 2 times 8. And its centroid is 6 plus half of 2 is 1 is 7. We're going to divide that by the areas. So that's going to be 12 times 3 is 36, plus 16 times 7 is 112, if I did my math right in my head. This is 12 plus 16. This is 28. Let me see if I did that right in my head. Yes, I did. So this is going to be 148 divided by 28, which is 5.3 centimeters. So this height from this baseline is 5.3 centimeters. I can then go on to find what is, I'm going to write it under here, what is my rectangular moment of inertia for this cross-section orientation? And we know it's the sum of I sub 0 plus AD squared. We have two sections, so we're going to have two calculations. This one's a rectangle, so it's 1/12 the base, which is 2, times the height, which is 6 cubed, plus the area, which is 2 times 6, times d, which is the distance from the neutral axis to its centroid. So 5.3 minus 3, and we're going to square that. Now we've got to take care of this second rectangle, and that's going to be 1/12. The base, which is 8, times the height cubed, plus the area, times the distance from its centroid to the neutral axis, which is going to be 5.3 minus 7. Square that. So we're going to do all that algebra, and hopefully somebody's way ahead of me and is doing that right now, and give me what the rectangular moment of inertia is for this cross-section in this orientation. So I'll wait just a second to see if anybody can come up with that number. If not, we can guess one and go forward since you know how to do it.
Professor, on this equation, where do you get the 5.3 minus 3 and the 5.3 minus 7?
Okay.
I just want to see like where you get it from.
We calculated the neutral axis to be 5.3 from the baseline. D is defined as the distance from the neutral axis to the centroid of the section that you're interested in. So this distance from here to here was 5.3. This part that I'm looking at, which is the 2 times 6, its centroid was at 3 from the baseline.
Okay.
So that distance is 5.3 minus 3, or what? 2.3. If I look at this guy, its centroid is going to be half of this. So I'm looking at the distance from the 5.3 to here, which was 6 plus 1 was 7. So it's 5.3 minus 7, and I'm squaring that. Anybody got a number for me yet? If not, I'll just invent one and we'll go forward. $45.6, okay? This is going to be times 10 to the minus 8 meters to the 4th. That's to account that we're putting it in centimeters in our calculation, but we need meters so we can come up with our proper units of megapascals. Anybody else get a number to compare that to? If not, we'll just go forward with that. Okay. So for section 1, I'm going to put this up here. We have a neutral axis of 5.3 centimeters. A rectangular moment of inertia of 45.6 times 10 to the minus 8 meters to the 4th. Any questions how we came up with that? All right. Now, let's calculate the neutral axis for my other moment, and then we have to do its rectangular moment of inertia. So I'm going to erase this. Okay. And now what I'm going to do is I'm going to take this and I'm going to lay it on its side. Doesn't make any difference which way you rotate it. Whatever you feel comfortable with doing. In this case, I'm just going to rotate it 90 degrees to the right. And so what I've come up with is I've just taken this and I'm laying it on its side. And what I ultimately want to come out with is I want to find out where is, for this shape, where is neutral axis 2? In order to do that, it's convenient, or it's best principles, to establish my baseline. Okay. Now, I want to find my neutral axis 2, which I know is going to be going this direction, or when I rotate it back, it's going to go in this direction. It is still the sum of my areas times its centroids divided by the sum of areas. Again, we still have just the two rectangles. So if I look at this guy, its area is 2 times 8. And from the baseline, what's the height of its centroid? Half of 8, which is 4. Then I'm going to have this guy, which is 2 times 6. And if this is centered, it's symmetric, then the height of its centroid from the baseline is 4. I then divide that by the sum of areas. And when I do all the math on that, times 4 is 64 plus 12 is 48 divided by 16 plus 12. That's going to come out to be, if I did that in my head right, that's going to be 4. So this neutral axis 2 is 4 centimeters from my baseline. All right. I now need to go back, so I'm going to write that up here. Neutral axis 2 was 4 centimeters. And then I'm going to go back and do the rectangular moment of inertia for this guy. So I'm going to erase this. So rectangular moment of inertia for 2 is equal to the sum of my I sub zeros plus AD squared, however many number I have, and I have 2 again. So let's do this guy first. It's a rectangle, so it's 1/12 the base, which is 2, times the height, which is 8 cubed, plus the area, which is 2 times 8. And now we need the distance from its centroid to the neutral axis. So the neutral axis is 4, but its centroid is also at 4. So 4 minus 4 is 0. 0 squared is 0, so that part drops out. Now we have to consider this part. Another rectangle, so it's 1/12 the base, which is 6, times the height, which is 2 cubed, plus its area, times its d. And its d is the neutral axis was at 4, but its centroid was at 4. So again, 4 minus 4 is 0. 0 squared is 0. That term drops out. So the rectangular moment of inertia for our second orientation is this little calculation added to that little calculation. So hopefully somebody can tell me what that is very quickly. $89.33, okay. Again, that's 10 to the minus 8 meters to the 4th. Okay, you now have all the information you need to find out anything of interest. Okay, so I'm going to erase all of this. Okay. Let's say I ask you to find out let's call this point A. Suppose I asked you, what is the plane stress? Because we know pure bending only creates plane stress. What is the plane stress at point A? using the principle of superposition, we can look at the plane stress caused by one bending moment and physically add to it the bending moment on the second. So let's go back. We initially did this neutral axis, which was caused by this moment. So this moment was 10,000 times the cosine of 25 degrees. The y value is the distance from the neutral axis to the point of interest. So my neutral axis here is at 5.3, and I want to go to that point there, which is 6. So this is going to be 6 minus 5.3. And this is Newton meters, and this is 10 to the minus 2 meters. So I'm looking for that distance. Everybody with me so far? Now I'm saying, what is happening due to this other moment? That moment is, well, let me fill in the rectangular moment of inertia. That was 45.6 times 10 to the minus 8 meters to the fourth. Okay? And when you look at this contribution, when I look at this neutral axis, everything above the neutral axis is in tension. So the sign of this is going to be positive. If we look at this side, what is the moment? That moment is 10,000 times the sine of 25 degrees. And again, that's going to be in Newton meters. If I look at y, y is the distance from the neutral axis to the point of interest. This is the neutral axis. So I'm interested in that direction. So that distance is 4. What is its rectangular moment of inertia for this other orientation? We calculated that to be 89.33 times 10 to the minus 8 meters to the fourth. And what is the sign of that, okay? Everything on this side of that neutral axis is in tension. So this value is plus. So this contribution is plus, this contribution is plus. So my final answer has to be plus. So if somebody has their calculator up and running, let me know what this value is, and then separately let me know what that value is. I'll see if I can do this at the same time. And then 10 to the minus 8, 10 to the minus 2, so this is going to be megapascals. This guy's going to be plus again. Whoops, I didn't do that first one right, sorry about that. $139.1. Anybody else get that number? Or if you didn't, let me know what you got.
I got that as well.
Okay? So if we do this part, 189.2 megapascals. Anybody get that number?
Yes.
Okay, so if we add those two guys together, that is 328.3 megapascals is the plane stress at point A. So if you know what material that is made out of, you can see if it fails. Any questions on how we did that? Well, let's pick another point. Let's pick,
Where was point A again?
point A is right at the end of the left-hand bottom part of that upper rectangle. All right, let's pick a different point. Let's pick a point 1 centimeter up from the baseline on this side of that one rectangle. And let's call this point B. Can I find the plane stress at point B? You betcha. I know it's going to be the moment 1 times y1 divided by I1 plus m2 y2 over I2. So we can go back and say, I already know what this is, and this is, because I've already calculated that. That moment is this same guy. Okay. This I is still that value. This moment is still that moment. Actually, let me use different colored here, just to try to keep these separate. This guy is the same as that guy. Okay, so that leaves us to, what is y1? Y1 is the distance from this neutral axis 1 to the point of interest. So I'm looking for, since this is the neutral axis, I'm looking for the distance from that neutral axis to the point of interest. And that's going to be, because I'm taking advantage of my baseline, 5.3 minus 1 times 10 to the minus 2 meters. Because this is 5.3 away from the baseline. This is 1 away from the baseline. So that distance is 5.3 minus 1. Everybody see how I got that? What is the sign of this contribution? If I go back, everything below the neutral axis is in compression. So this value is negative. Let's go back and look at this y2, and that is the distance from this neutral axis to the point of interest. So I'm going from this neutral axis to here. So if this is too wide and the neutral axis was exactly at the middle, that distance has to be 1. Okay. And then if I'm looking for the sign on that one, this point, when I look at this neutral axis, everything on this side is in tension. So this is a plus. So let's see what we get for an answer. You can work this hopefully out at the same time I'm doing it. at 854.6 megapascals. The sign is negative. If I do this side, I got 47.3 megapascals. And again, this sign was positive. So when I add these two together algebraically, I get the stress at point B is minus 807.3 megapascals. So that is the plane stress at this point right here. I know it's compressive, and I can look to see this compared to the yield value for that material to see whether it would fail at that point. So we can pick any point that you want on here. We could pick .5 centimeters over and 0.5 centimeters down and call that point C. So can I ask you to find the plane stress at point C? Yes. Superposition? This value is the same as this value. This value is the same as that value. This value is the same as this value. This value is the same as that value. So the only thing we really need to do is define a value for y and then get a sign that goes with it. So if we look at the orientation that created this moment, which is this neutral axis, the distance from my neutral axis to the point of interest, that distance is, from here to here is 5.3. The distance from the baseline to here is going to be 6 plus 2 is 8 minus 0.5, which is 7.5. Doesn't make any difference if this is a plus or minus sign. All you're interested in is the absolute value. So this value would be 2.2 times 10 to the minus 2 meters. Because again, I'm interested in the direct distance from this neutral axis to there. And what is the sign? This point, as far as this is, it's above the neutral axis, it's in tension, so this value is plus. If we look at the last one, okay, what is y2? And again, what is y2? It's the distance from this neutral axis. So this was at 2. Excuse me. This was at 4. And this distance was 2.5 in. So you need 1.5 from here to here, from this neutral axis to the point. And what is the sign? Everything on this side of the neutral axis is in compression. So this would be a minus. Do this algebra, that's going to be a plus value. Do this algebra, it's going to be a negative. Algebraically add these two together, and that is the plane stress at point C. So you can find it anywhere in that. Okay, you guys, any questions on that? So you guys are now masters of multi-axial bending. Didn't take that long at all because you understand what you're doing for uniaxial bending. Any questions on that? I'm going to cover one other quick topic on this, and then I want to cover a little bit of stuff that you might need to know for the experiments tomorrow at URI. Any questions on what I've done here? Okay, I'm going to erase this, but I'm going to go back to that initial sketch. I'll make it a little bit more complicated. Okay. It's 2 and 6, 2 and 8, and this side is 6. So now we have 3 parts, okay? So if I gave you multi-axial bending, you can go back and know I'm going to end up with something that looks like this. So this is my neutral axis 1, which is going to be going in this direction. And just looking at this, curl towards compression, compression, tension. And this is for neutral axis 1. If I look at this guy, you know the neutral axis is going to be going in this direction. Neutral axis 2, curl, curl. So this side is in compression, this side is in tension. Always do that to set up so you'll know where your tension and compression areas are. Okay? And we can do all the math that you needed to do to find the stress at any point. But now I'm going to throw something different in there. I'm going to say that this section is made out of aluminum 1100. I'm going to tell you that this section is made out of annealed yellow brass. And let's make the top section structural steel. So now we have different materials. And now let's say I want to know what is the stress at point A. It's still going to be by the principle of superposition. Okay. Except we have to modify the cross section. So to do that, to modify the cross section, we look at ratios of E, where E was a modulus of elasticity. When we do that, we select one material, and usually you pick the one with the lowest value of E. Then we make E ratios then multiply that ratio times the width only for that section. So what does that mean? Let's go back and look at this. We have established our three different materials. So hopefully you can see down here. So I'm going to go back, and the E value for my aluminum, if you look on our little table, is 70 gigapascals. If I look at the E for my annealed yellow brass, again on our table, that value is 120 gigapascals. If I look at E for my structural steel, that value is 200 gigapascals. So does it make any difference which one of these we use as sort of our common denominator? No. But it typically, you use the lowest one just to make your numbers come out one or greater rather than a fraction. So if we do that, the ratio of annealed yellow brass to aluminum is 120 to 70, and that value is 1.714. If we look at the ratio of structural steel to E aluminum, that value is 200 divided by 70, and that value is 2.857. And then, of course, you look at the aluminum by itself, and 70 divided by 70 is 1. Now you're going to go back and adjust the widths only for our cross section. So this section is annealed yellow brass. Its value is 2, but we need to multiply that times 1.714. So that value comes out to be 3.428. So this balloons up and looks like this. This side is 3.428. This side is still 6. Everybody with me? Now we go back at our aluminum 1100. That was our common denominator. So we're going to multiply that width times 1, so nothing changes there. Then we're going to go up and look at our structural steel, and this width, which was 8, we're going to multiply the 8 times 2.857. I have that value come out to be 22.86. So this 8 now becomes 22.86. We're not changing the height, so you now have a much broader triangle. So now, when you go to calculate neutral axis 1, you have this new shape. This one didn't change. You have this new shape to come up with the neutral axis. When you come out to find the rectangular moment of inertia, you have this shape, and this shape to come up with that value. Okay? If you put a multi-axial bending on it. We have to turn this guy sideways. So we started out like that, where this guy was 6, this is 2, this is 2, this is 8, and this is 6, okay? Now in this orientation, we have to go back and adjust the widths. This guy was annealed yellow brass, its value was 6, but we're having to change it by 6 times this. And I had that come out to be 10.28. So this width, instead of 6, now becomes 10.28. The middle section is aluminum 1100. Its width does not change because that's our common denominator. And then the other guy, its width of 6, it changed by 2.837. So I had that guy come out to be 17.02. So this width becomes, instead of the height of 6, this becomes 17.02. So we have a different looking triangle. We still have a rectangle, we still have a rectangle, and we have a different triangle. So again, now with this shape, you calculate its neutral axis 2, you find its rectangular moment of inertia. When you found all those values, you can go back, use this equation to find the plane stress anywhere of interest. When you do this, let's say this value came out to be wherever A is, or let's say A is here. Let's say that value came out to be, I'm just going to invent this. When you did all of this, it comes out to be minus 82.6 megapascals. Okay? To see if the system is safe, you then go back and use the yield value for your common denominator. And a common denominator was aluminum 1100, and we know that that value is 95 megapascals. It's in compression, but it's still less than that, so it is safe.
Where did we get the 82.6 megapascals from?
I just invented that. That's after you go, because we didn't calculate the neutral axis, we didn't calculate the rectangle, we didn't do any of that. I told you how to do it, just like we did before, and I'm just inventing a final number. So no matter where I pick a number to start with, if I ask you, this is, if this is point B, okay, point B here comes out to be point B there. You put in your values, you do all your number chugging here, you come up with a value, and since we've selected aluminum 1100, you compare whatever this value is to the yield value to see if it's safe or not. If you converted it all to anneal yellow brass, we compare whatever point you pick to anneal yellow brass. There's a fair amount of number crunching, but I think the concept is fairly simple. Any quick questions on that? Okay. If not, I have a quiz for you on this. Let me send that to you now, and then I'll go over that one with you. Okay, I just sent that one to you. So I'll wait till you get it, and then I'll go over it with you.
Professor Sherrard.
Yes,
Okay, so we're creating these new dimensions for these shapes just to get our I value, is that correct?
and the neutral axis.
Right, and the neutral axis. But then if we had a point on there, we would go back to the original dimensions for the shape?
No, you go to the adjusted dimensions.
Okay, so would we marry those two together so that we have new dimensions all around?
Okay. When you're doing this equation, if I'm looking at that contribution, I'm going to go, since I established a neutral axis in this direction, I'm going to use that moment on this adjusted cross section with its adjusted rectangular moment of inertia, and the y is going to be wherever that neutral axis is to my point of interest, which is here. Then when I go to calculate this contribution, I know that that's caused by this neutral axis. So I'm going to use that moment, that rectangular moment of inertia that I got from this orientation, and then wherever my A is here, I would find A from this dimension. In other words, use just the moment, neutral axis, Y bar, I bar for each modified section. This one would use M2, neutral axis 2, Y2, I2.
Okay, thank you.
So this guy goes with this orientation, this guy goes with this orientation. But it's still the same concept. In other words, if your neutral axis goes through here, you're looking at that distance from the neutral axis. Just like here, the neutral axis, you're looking at wherever that neutral axis is. It could be up here. You're looking at that distance. And what I did is I gave you the same shape, which is a semicircle, the rectangle, and the triangle that we've been using for quite a while. So that's going to make some of that easier for you. So I've asked you, what is the plane stress at point Q, which is the left-hand edge of your semicircle? And then I've asked you, what is the plane stress at R, which is that inside notch where the rectangle joins the triangle? And at that particular point, all you're doing is finding out the stresses, which is what we did earlier. And that's worth 12 points. I then ask you Where is the plane stress exactly equal to 0? Tell me where that is, prove where that is, whatever you want to do. And then I'm asking you, if our system is aluminum 1100, it's all one material, is our system safe? And I've made that worth more points, 8 points, because that's a little more difficult than you think it is just looking at it. And part of the rationale is there, you have to find out where the maximum value for tension occurs, and where the maximum value for compression occurs, because this is multi-axial bending, and that's a little bit more complicated. But if you do tackle that, that's worth 8 points extra. Any questions on the quiz? This will also be due on Wednesday. We'll go over that. And then on Wednesday, I'll primarily give you time for any review you want to do on nuclear material science, because on the following Monday, we'll have the exam in class. If we have any time left over, I'll do a little mini review for reactor theory. And then when we meet the following Monday, if there's any other little review you want to do for reactor theory exam, we'll do that. And then I will give you the reactor theory exam, go over it, and that'll be due after Thanksgiving. And then I'll give you the nuclear material science exam number 3, go over that, and then that'll be due by the end of class next Monday. Okay? Anything on that? If not, I want to spend a couple of minutes on information that you might need or you will need for the lab tomorrow and Thursday. Okay, what I'm going to do now is I'm going to start into chapter 10, which is dynamic reactor, which means the rate of change of the neutron population with time is not 0. It's not steady state. One of the things we have to discuss is something called neutron lifetime. And this is the time a neutron exists from birth, which means a thermal fission, to thermal absorption, to start the cycle going again. It's 3 parts. We have L is equal to a lifetime due to birth, plus a lifetime due to slowing down, plus a lifetime due to, if you would, thermal travel. Remember we found before L, which is thermal diffusion length? That's the distance the neutron travels between when it becomes thermalized and when it gets absorbed. This is the distance that travels over that time. So, no matter what you have for a fissioning fuel, this value is about 10 to the minus 14 seconds. It is really quick. This is typically something on the order of 10 to the minus 6th to 10 to the minus 4th seconds. And slowing down means you create this neutron at some energy from a thermal fission. And remember, for uranium-235, that energy is 2 MeV. So How long does it take to go from 2 MeV with all the scatters that you need to get it down to thermal? It takes 10 to the minus 6 to 10 to the minus 4th seconds. And this is solely a function of the moderator. Different moderators will take longer or shorter time. The thermal travel is typically on the order of 10 to the minus 2 seconds. So when you look at the lifetime of a neutron, the birth is very short. There's also a short moderation time, relatively short thermal time, but in reality, thermal diffusion length is pretty closely tied to the travel time. Okay. And again, we're going to go in depth on that later. Just wanted to present that concept to you. The next thing is excess reactivity. Okay. If at steady state, we know that K effective is exactly 1. If we want to go up in power, down in power, we have to change K effective. And excess reactivity is looking at K effective minus 1. And you can follow this in your textbook. At the start of chapter 10. So K effective minus 1 is whatever you have for a change in K effective. And this could be a positive or a negative value depending on if you're going down in power or up in power. We then introduce rho, which is not, unfortunately, density, but this is equal to delta K effective over K effective. This is reactivity. This is either positive or negative, or it could be 0 at steady state. Typically, we operate a reactor around steady state, so K effective stays near 1. So if this is around 1, then effectively reactivity is delta K effective. This again is called reactivity. It is dimensionless. This K effective is dimensionless, but we have units for it. It is either called in hours for reactivity, or it can be in dollars. And the reason they typically use in hours as the unit, they might ask, what reactivity do you have to add in order for a reactor to have a stable reactor period of exactly 1 hour? Depending upon what the fuel is, you could get the answer in dollars. I'm going to go over that probably week after Thanksgiving. I just wanted to give you that basic definition of excess reactivity, which is delta K effective, how you come up with reactivity, and the fact that it could have two different units. So for example, if you are going to go up in power, we know that we have two ways to do that. We could pull rods, or we could dilute. Okay. If you're doing this, you're considering that you're adding positive reactivity. And we can relate that back to K effective. And again, whenever you get to where you want to go, things will stabilize back out and your K effective is back to 1. If you go down in power, we say you're adding negative reactivity, and you do that again by inserting rods or adding boron. But we're going to cover that more later. The final thing I wanted to discuss with you, actually 2 additional things. Any quick questions on that? And again, Jeff will probably be lecturing to you tomorrow on this topic, but at least hopefully you'll have a little bit of understanding. Normally we would not do these experiments tomorrow until after Thanksgiving, but again, we have to go with what they can support us with. The 2 final things I wanted to mention, one was T, capital T, which is defined as reactor period. Reactor period is defined as the time it takes to change the flux by a factor of E. And that E is the same, for example, when you did decays, that's that same E right there. So, in normal reactor operation, if you are at K effective equals exactly 1, what do you think my reactor period is? Any guesses?
1 second.
No. It's actually at infinity because K effective equal 1 is steady state. Okay? Now, when you're operating to move your reactor up in power, down in power, do you think you want, when you accomplish this, do you think you want a short reactor period, a long reactor period, or it doesn't make any difference? So for example, if you're operating this, let's say you're going up in power, would you like your reactor period to be 100 minutes or 2 seconds, and why? Any guesses there? Okay.
I would guess 100 minutes, so there's not a shock to the system.
Okay, that is the correct answer. And the reason why is reactor period is the time it takes to change a flux by a factor of E. So if I have 2 seconds, that means every 2 seconds I'm going to change the flux by a factor of E. So if I look at just 10 seconds of time elapse, that means that is 5 reactor periods. So that is E to the 5th. So your flux has changed by e to the 5th. And that value is 146 times the original flux. 10 seconds is nothing in time. So what happens is if you have very short reactor periods, this reactor control can get away from you before it ever happens. So you're typically operating with long reactor periods so that you can actually control what is going on. Whenever you have shut a reactor down for any reason, it's scrammed, controlled outage, whatever, there is on the thing a reactor period meter. And when you start the system back up, there will be protocols that tells you what you can have for a reactor period. If you get a shorter period than designed, you must immediately shut down and start over again. If your reactor period meter is broken, you cannot start the reactor back up again until the NRC comes and physically inspects things to make sure the thing is not going to get away from you. Like we had an incident going back about 15 years ago when we were using a reactor up at WPI, well, they still had theirs, where their reactor period meter broke, and we could not go up for experiments until the NRC came. They did all the testing to make sure that the meter was properly recording what was going on. Okay. So I just wanted to let you know that concept. And then the final thing is, when we look at thermal fission neutrons, we know that, for example, for U-235, whenever it fissions, we have around 2.5 neutrons, and these are fast, created at a thermal fission. And we want to get these guys, and they're again at about 2 MeV. We need to get these down to thermal value 0.0253 EV in order to cause an excellent. We call these prompt neutrons. And this accounts for about 99% of all neutrons. But we also have delayed neutrons. This accounts for about 1% of the total. And the delayed neutrons come from the natural decay of fission fragments. So if you remember back when we had uranium-235, we went to uranium-236, and then we had fission fragment 1 plus fission fragment 2 plus, on the average, 2.5 neutrons plus kinetic energy plus gamma. And there were, for uranium-235, there were 16 preferred pairings. So let's say this pairing was iodine and copper. I'm just inventing those, okay? These could be, and probably are, radioactive, so they will want to decay to a stable state. Certain ones of these fission fragments, as they're decaying down, rather than producing an electron, rather than producing a positron, alpha particle, whatever, they can decay by giving off a neutron as they want to go stable. This is a delayed neutron because it will occur after the main fission as these fission fragments are decaying. The fact that they're coming in later produces more neutrons, which is better for you for criticality. And also because they're coming in later, it allows you better control of the reactor. These are physical properties of the decay products. And to be honest with you, if we did not have delayed neutrons, commercial nuclear power as we know it would not be possible, because the neutrons that come from the direct fission are too energetic and occur too rapidly for you to control in a meaningful manner. That's all I'm going to do today. I will see you there. I plan to get there to URI tomorrow. For those of you going tomorrow, I plan to get there about 9:45. Again, bring your photo ID, bring your mask. I would encourage you to bring your textbook, a notebook, and your calculator, and you ought to be all set. I will be here today probably till about 6 o'clock or so, grading the quizzes you gave me today. If you need to see me on anything, the only other thing I want to say is, Joel, are you still here? I don't see your name up there, so you might have left. Anyway, there's still 2 of you that have not registered. I encourage you to do that sooner rather than later, because very soon I lose control of seats in classes that are not nuclear. So for example, come the 1st of December, I will no longer have control of the seats in heat transfer and thermal science. Those revert back to the general population, so anybody in mechanical can ask for and move into those seats. And if those sections fill up, you're out of luck. Normally when I start a semester, I ask for key courses for the first month can only be filled by nuclear students. So when you were here as freshmen, the chemistry class, the physics class, 25 seats in the pre-calculus class were earmarked for just nuclear students. Nobody could sign up for those for 1 month. And then if you didn't do it, then it went out to the general public. You might find yourself, you couldn't get into a chemistry class or a physics class. So the 2 of you that haven't registered, I strongly encourage you to do that as soon as possible. Other than that, sir, I'm going to ask you if you could either stay on the line for just 1 minute, or else call me back today after Professor Lance's class. Other than that, I'll see half of you tomorrow at URI.